When you think about the great invisible forces that shape our physical world, you probably picture gravity pulling the planets into orbit.
Right, or maybe tectonic plates crashing together in slow motion to build mountain ranges.
Exactly. Big, massive, heavy things.
Yeah.
But right now, at this exact moment, inside your body, all around you, anywhere on this planet where there's a drop of water, there is a completely invisible, silent force dictating life and death.
And it's happening on a cellular level millions of times a second.
Yeah, it really is. Today, we are unpacking the hidden thermodynamics of osmosis.
It is entirely invisible, yes. And yet the stakes could not be higher for you. Every single time you drink a glass of tap water, you are essentially initiating a thermodynamic pressure war in your bloodstream.
A pressure war. I love that phrasing.
It's true. If this mechanism stopped working for even a fraction of a second, biology as we know it would catastrophically fail. Your cells would either violently explode or shrivel up into tiny raisins.
Which brings us to our mission for this deep dive. We are using a comprehensive breakdown of osmosis to rescue this concept from whatever vague, stuffy memories you might have of staring at a high school biology chalkboard.
Right, because it's so much more than that.
It is. We are going to reveal osmosis for what it truly is, which is a relentless, unstoppable physical engine. It explains why your houseplants stand upright, why table salt is like a lethal weapon to a garden slug, and how pure water essentially bulldozes its way through microscopic barriers.
It really is the ultimate biological tightrope walk.
Okay, let's unpack this. Because to understand how it works, we have to look at the foundational mechanics first.
Right. So osmosis, at its core, is the spontaneous net movement of solvent molecules. And in biological systems, that's almost always water.
Just water doing its thing.
Exactly. These water molecules move through a selectively permeable membrane. They travel from a region of high water potential to a region of low water potential.
Like a low.
Yeah. The entire driving desire of this physical system is just to equalize the concentrations on both sides of that barrier.
Let's unpack that concept of water potential for a second, because that phrasing can sound a bit backward to people.
But it definitely can, yeah.
It's easier to think about it in terms of the stuff dissolved in the water, right? The solute. Like water wants to go where the party is.
That's a great way to look at it.
If one side of a barrier has a massive concentration of dissolved salt, and the other side is mostly pure, uncrowded water, that pure water is going to rush across the barrier to balance out the ratio.
Precisely. The pure water is driven to dilute the highly concentrated side.
Think about a simple slice of potato dropped into a glass of heavily salted water.
Oh, the classic potato experiment.
Right. So the water trapped inside the potato cells is relatively pure compared to the extreme salinity of the glass. Because of osmosis, the water inside the potato realizes it's drastically outnumbered by the salt on the outside.
It's a localized imbalance.
Yeah, so it rushes out of the potato through the cell membranes and into the glass. It is this microscopic tug-of-war for water, and the heavily salted environment wins.
And as a result, the potato loses all its internal water pressure, and it just shrinks. It loses its turgor pressure.
It's wild. And what's truly fascinating is how long human beings have recognized and utilized this effect.
Oh, absolutely. Centuries before anyone had the microscopic tools to understand the cellular mechanics, the localized flow of water driven by salt gradients was observed as far back as the construction of the Egyptian pyramids.
Wow, really? The pyramid?
Yeah, but the first properly documented scientific observation didn't happen until much later. It was 1748 by a French physicist named Jean-Antoine Nollet.
Nollet's experiment is just a wonderfully bizarre piece of scientific history.
It really is.
So picture this. Nollet takes a cylindrical glass vial and fills it to the absolute brim with alcohol.
To the very top.
Right. Then, instead of sealing it with a cork or a glass lid or something normal, he takes a piece of damp pig bladder, stretches it over the neck of the vial, and ties it down incredibly tightly.
As one does in the 18th century.
Naturally. And finally, he takes his whole contraption and completely submerges it in a large basin of pure water.
He does this to ensure no air can interfere with the boundary. So he leaves it submerged for about 5 or 6 hours.
And when he comes back to check on it,
the result completely shocks him. The vial, which remember was already completely full of alcohol, is somehow holding even more liquid.
Silver-filled.
Exactly. The pig bladder acting as the cap wasn't just bulging upward, it was stretched to its absolute physical limit.
The pressure inside that glass vial had become so immense that when Nollet took a sharp pin and pricked the top pig bladder, a pressurized jet of alcohol shot out over a foot into the air.
It is a phenomenal visual of thermodynamic force in action.
A foot into the air, just from water pushing in.
Yeah. The pure water in the basin was crossing through the biological membrane of the pig bladder in a relentless attempt to dilute the alcohol inside the vial.
So the water could get in, but the alcohol couldn't get out.
Exactly. The water could easily push its way in, but the larger alcohol molecules couldn't push their way out. This created a massive compounding buildup of internal pressure.
And that buildup of pressure, that literal physical forcing of water, eventually gave us the name we use today.
Right, the etymology is really interesting.
A few decades later, another French physician, René Dutrochet, was studying this exact phenomenon. He combined the Greek words for within and outer with the word ismos, which literally translates to push or impulsion.
The push.
Yeah, so you had endosmos and exosmos, which eventually merged into the term osmosis.
That etymology of the push is scientifically perfect because Nollet's pig bladder wasn't just an eccentric parlor trick.
No, it wasn't.
That piece of dead animal tissue perfectly mimics the selectively permeable membranes that wrap around and protect every single living cell on Earth today.
Right, which brings us to how this actually operates inside living things.
The biological border control.
Exactly.
Yeah.
If we look at the cellular level, biological membranes act like incredibly strict border control. They are made of phospholipid bilayers. You have these molecules with water-loving heads and water-fearing lipid tails sandwiched together.
And because of that oily, hydrophobic core, these biological borders are generally completely impermeable to large molecules.
Or to anything carrying an electrical charge,
Yeah,
right?
so polar molecules, stray ions, large proteins, complex sugars, they hit the membrane and just bounce right off. They cannot cross without an active transport mechanism.
But nonpolar molecules can get through.
Yeah, nonpolar molecules like lipids or tiny dissolved gases like oxygen can slip right through the cracks.
But wait, water is a polar molecule. It has a slight positive charge on one end and a negative charge on the other.
That's true.
So logically, water shouldn't be able to easily cross that oily border control either, right?
It really shouldn't. If water had to rely purely on squeezing through the lipid bilayer, osmosis would happen far too slowly to sustain complex life.
So how does it work?
Nature evolved a brilliant workaround. Water sneaks through the barrier via highly specialized protein channels called aquaporins.
Aquaporins.
Yeah, you can think of them as selective pore flow mechanisms.
They're like a biological VIP entrance.
That's a great analogy.
A dedicated fast-pass lane exclusively designed to let water molecules flow in and out of the cell at staggering speeds, driven entirely by osmotic pressure while keeping everything else locked out.
Exactly. And plants are the absolute masters of exploiting this VIP entrance.
Oh, they rely on it completely.
They do. When water enters a plant cell through osmosis, it creates something called turgor pressure. This is the exact same pressure that stretched Nollet's pig bladder to the breaking point.
So the water rushes in and pushes outward against the plant's rigid cell wall.
Right, and that internal water pressure is literally the structural support that keeps a soft-stemmed plant standing upright toward the sun.
So when a plant cell is sitting in an environment with plenty of pure water, like a hypotonic solution, the water relentlessly pushes in.
Yes, and the cell swells up tight against its rigid wall, becoming what botanists call turgid.
Turgid. Fully hydrated and stiff.
But if you subject that plant to a hypertonic solution, say a flood of salty seawater, the osmotic gradient flips.
The water runs away.
Exactly. The pure water inside the plant cell aggressively rushes out to dilute the salt in the soil. The cell shrinks, becoming flaccid.
And if the salt concentration is too high?
If it's high enough, a violent microscopic event called plasmolysis occurs. The plant loses so much internal pressure that the inner cell membrane actually tears away from the rigid outer cell wall.
Yikes. That effectively kills the tissue.
It does. It's fatal for the cell.
Okay, wait, this brings up a really crucial distinction. Plant cells have those thick, tough cellulose walls to act like a pressure vessel.
Right, they have structural reinforcement.
They can handle that massive influx of water pressure. But human cells don't have rigid plant cell walls to protect them. Our cells are just like squishy little balloons of membrane.
Very squishy, yes.
So what happens to us if the balance is off? Why don't we just pop?
Well, the reality is that human cells are incredibly vulnerable because of that exact lack of a rigid cell wall. We are terrifyingly sensitive to both dehydration and overhydration.
The forces at play are just immense.
They are. If you place a human red blood cell into a hypotonic environment like a beaker of pure distilled water, The water will rush into the cell so fast and with such thermodynamic force that the cell membrane simply cannot contain it.
Because there's no wall to stop the expansion.
Exactly. The cell undergoes cytolysis. It violently swells and bursts.
The structural integrity just completely fails.
Complete failure. Poof. Conversely, if you drop that same red blood cell into a hypertonic environment like extremely salty water, all the water inside the cell violently rushes out.
Trying to dilute the salt outside.
Right. And the cell rapidly shrivels up into a spiked, dysfunctional shape. This is exactly why medical IV fluids aren't just pure water. They are meticulously formulated saline solutions.
You need that perfect balance.
Maintaining an isotonic environment where the concentration of dissolved solutes inside and outside the cell is perfectly, precisely balanced is a minute-by-minute requirement for human survival.
It really reframes how you look at biology. Osmosis is an engine for life, but when the environment shifts, it becomes a remarkably swift killer.
Oh, nature has some grim examples of this.
Yeah, I was looking at the text, and there's some notoriously dark examples, like if a storm surge drops a freshwater aquarium fish into a highly saline saltwater puddle.
The maladaptive salinity kills it almost instantly.
Because the water inside the fish's cells desperately rushes out to dilute the ocean.
Right, and the animal fundamentally dehydrates while completely submerged in water.
It is a brutal paradox, dehydrating while underwater.
It really is.
And then there is the classic, slightly cruel garden example, pouring table salt on a slug or a leech.
Oh, the visual is very visceral.
You pour the salt, and the slug immediately shrivels and foams.
Yes, it's a very vivid demonstration of osmotic harm. When you pour salt onto a slug's highly permeable skin, you are artificially creating a massively hypertonic environment right on its surface.
So the pure water inside the slug rushes out.
Exactly. The relatively pure water inside the slug's cells rushes out across the membrane to try and dilute that localized mountain of salt. You are weaponizing osmosis to fatally dehydrate the creature in a matter of seconds.
And it's so easy to picture what's happening there as the salt actively sucking the water out of the slug, right? Like a dry sponge soaking up a spill.
That is the mental model almost everyone has.
The salt pulls the water.
Right.
But and here's where it gets really interesting. We have to completely dismantle that idea. Because that mental image, the idea of salt sucking or pulling water across a barrier, is actually a massive scientific misconception.
It is entirely wrong, conceptually.
Completely wrong.
The actual physical mechanism driving osmosis is heavily misunderstood, even by people who work in adjacent scientific fields.
So what are people getting wrong?
Well, people usually rely on one of two incorrect models. The first is that the solet, like the salt, is simply diluting the water, so the water naturally just diffuses from where it's highly concentrated to where it's less concentrated.
Sort of random particles bumping around until they spread out evenly.
Right, simple diffusion. The second misconception is the bound water model, which is the sponge idea you just mentioned.
That the salt is magnetically pulling it.
Exactly. This is the assumption that the salt molecules somehow reach out with a chemical magnetic force binding to the water molecules and physically dragging them across the membrane.
But both of those intuitive ideas are conclusively false based on the thermodynamics.
Yes, they are.
The diffusion idea is broken because under certain thermodynamic conditions, osmosis can actually drive water across a membrane toward a higher concentration of water.
Which completely violates the rules of simple diffusion.
Right. And the attraction idea, the sponge model, is wrong because osmosis is what physicists call a colligative property.
That is the crucial pivot point right there.
A colligative property.
Yes. A colligative property means the physical effect depends absolutely and purely on a number of dissolved particles, the raw molar concentration, and it has absolutely nothing to do with their chemical identity.
So the water doesn't care what is dissolved in it.
Exactly. It doesn't matter if the solute is salt or glucose or some synthetic polymer. It doesn't matter how hydrophilic, how much it loves water, the solute is.
So it could be a chemical pull.
Right. If it were about chemical attraction or magnetic pulling, the specific chemical identity of the solute would change the force of the pull. But it doesn't. 100 particles of salt generate the exact same osmotic pressure as 100 particles of sugar.
Okay, I have to stop you and push back here, because this is where my brain starts to hurt.
It's a lot to wrap your head around.
If the solute isn't pulling the water, and it's not just simple diffusion, then what invisible hand is actually driving this car? Why does the water move with enough force to explode a blood cell?
To understand the why, we have to step out of biology entirely and dive into thermodynamics.
Okay, let's do it.
You cannot explain osmosis accurately without looking at the mechanical forces between molecules. The true explanation involves a principle called the virial theorem.
The virial theorem. Let me see if I can translate this because it gets deeply counterintuitive.
Go for it.
Tell me if I had this right. Think of the pure water molecules on one side of a membrane, like a room full of toddlers running wild.
Okay, I like this.
They're bouncing off the walls, bumping into each other, creating a ton of kinetic energy and high pressure.
A chaotic, highly active system, yes?
Now, on the other side of the membrane, you have salty water. You've added solute molecules.
Yeah.
Instinctively, you'd think adding more stuff to the room would increase the pressure.
Because there are more bodies in the room?
Right? But the virial theorem says it's the opposite. Adding the solute is like adding adults into that room full of toddlers.
Oh, that's clever.
The adults grab the toddlers' hands. They're physically attracted to each other, which calms the whole room down. The toddlers stop bouncing off the walls as much. The overall pressure on the walls actually drops.
That is a brilliant way to visualize it. The intermolecular attraction between the water molecules and the solute molecules actually reduces the overall thermodynamic pressure of the system.
But lowers the pressure.
Yes. The pressure exerted by the water molecules on each other in the salty solution is objectively less than the pressure exerted by the wild, free-bouncing molecules in the pure water.
So because the pure water side has more wild toddlers bouncing around,
the pure water physically pushes harder against the membrane.
Because its internal mechanical pressure is higher.
Exactly. The pure water essentially forces its way into the lower pressure salty side. The salt isn't pulling the water in. The pure water is aggressively bulldozing its way across the membrane to escape its own high-pressure environment.
Escaping.
Yes. It will keep bulldozing until the pressure on both sides reaches an equilibrium. It is a pressure-driven process of viscous flow, not just random molecular diffusion.
That fundamentally flips the whole concept upside down for me. It's not a pull. It's a relentless push.
A relentless push.
And this leads to an absolutely staggering realization about energy. When that pure water bulldozes its way in and forces liquid to rise up against gravity like shooting alcohol out of Nolet's pig bladder, it is performing physical work.
It is.
It is literally converting ambient heat from its surroundings into mechanical energy.
That is the thermodynamic beauty of the system. The kinetic energy of the water molecules, which is derived from the ambient temperature of the room, is being harnessed and converted directly into the mechanical work of moving mass and generating pressure.
It's an engine.
Osmosis isn't just a biological quirk. It is a naturally occurring thermal engine.
And if pure water is relentlessly bulldozing its way across membranes, generating massive mechanical pressure and heat, well, humans are never going to just let a natural engine sit there unexploited.
No, we certainly wouldn't.
If nature built a pressure engine, engineers were always going to figure out a way to harness it for our own technology.
And we have, quite successfully, though our most famous application involves fighting a brutal war against it.
Right, reverse osmosis.
Yeah.
We hear this term constantly in the context of water filtration and desalination plants.
It's everywhere.
If natural osmosis is pure water bullying its way into salty water, reverse osmosis is humanity fighting back with brute force.
Very stubborn brute force.
I always think of it like biological bouncers at a nightclub. You have a barrier, the membrane, and a massive crowd of salty, undrinkable seawater on one side.
And natural osmosis dictates that any pure water on the clean side should rush over to join the salty side.
Which is the exact opposite of what a desalination plant wants.
Exactly. We want the clean water separated.
So instead, we apply massive, overwhelming external mechanical pressure to the salty side. We push so incredibly hard with industrial pumps that we overcome the natural thermodynamic pressure.
We overpower the engine.
Yeah, we force the water backward through the membrane. The pure water gets squeezed to the clean side, and the unwanted salt is left behind, like kicking out unruly guests at the door.
It's an incredibly effective way to turn unpotable seawater into clean drinking water, which of course is vital for global infrastructure.
But there's a catch.
Right. There is. Because you are actively fighting a fundamental thermodynamic force, it requires immense amounts of electricity to run those high-pressure pumps.
It's expensive.
Very. However, engineers are now perfecting a fascinating, much more energy-efficient variation called forward osmosis.
Forward osmosis. where we stop fighting the engine and let it do the work for us.
Precisely. Instead of using blunt force mechanical pressure, forward osmosis uses a highly concentrated draw solution to coax the water through the membrane naturally.
How does that work in practice?
Imagine you have a tank of heavily contaminated, dirty water. You place a membrane in the middle. On the clean side, you place a draw solution that has a phenomenally high osmotic pressure.
Way higher than the dirty water.
Exactly. The pure water from the contaminated side naturally bulldozes its way across the membrane to dilute the draw solution, leaving all the heavy metals and bacteria behind. No massive electrical pumps required.
Wait, let me think through the logistics of that.
Yeah.
If you use a highly concentrated draw solution to pull the pure water out of the toxic water, aren't you just trapping your newly clean water inside that highly concentrated draw solution?
You are?
If you use salt, you just turn toxic water into salt water. Are we just replacing a dirt problem with a salt problem?
That is the exact engineering hurdle. In industrial setups, you often have to do a secondary thermal separation step to remove the draw solute, though it still ends up being more energy efficient overall.
Okay, that makes sense.
But there is a brilliant alternative for specific use cases. What if your draw solution is made of something you actually want to consume? What if you use a highly concentrated ingestible glucose syrup as your draw solution?
Oh, wow. So the pure water bulldozes across the membrane, filtering out the deadly pathogens from the floodwater, and it dilutes the glucose syrup.
And you don't even bother separating it.
You just drink the resulting sugar water directly. That is an incredible application for disaster relief or like military survival gear.
It is incredibly elegant. And if we connect this to the bigger picture, the applications are scaling up in ways that sound like science fiction.
Tell me more.
Beyond filtration, the real frontier is salinity gradient power. Think about where a massive river empties into the ocean. You have a colossal volume of pure fresh water relentlessly crashing into a massive volume of highly concentrated salt water.
The ultimate osmotic imbalance.
Exactly. The difference in thermodynamic pressure between those two bodies of water holds a staggering amount of potential energy.
We can harvest that?
By directing that spontaneous natural mixing across specialized semi-permeable membranes, we can harness that bulldozing force to spin turbines. It presents a completely sustainable, continuous, renewable energy source.
That's amazing.
It doesn't rely on the sun shining or the wind blowing. It just quietly runs on water's relentless desire to balance its own internal pressure.
So what does this all mean? We're literally running power plants on water's desire to mix.
Yes, and researchers aren't just looking at macro-level infrastructure either. On the microscopic scale, medical engineers are using these exact same thermodynamic principles for precise drug delivery inside the human body.
Really? Like osmotic implants?
Exactly. They are manufacturing tiny implantable capsules.
Wow.
Once inside you, the natural osmotic pressure of your own bodily fluids forces pure water into the capsule.
Which pushes the medicine out.
You got it. It slowly and mechanically pushes liquid medication out into your bloodstream at a perfectly steady, controlled rate. No batteries, no moving electronic parts, just pure thermodynamics.
It's a profound journey. From generating zero-emission power for coastal cities to delivering life-saving chemotherapy drop by drop.
The engineering applications of this invisible biological force are expanding at an astonishing rate.
We started this deep dive with a shriveling potato slice and a French physicist accidentally shooting alcohol across a room in 1748. And by simply asking why the water moves, we've ended up at the absolute bleeding edge of global water sustainability, renewable energy engineering, and targeted nanomedicine.
It's quite the evolution.
It really forces you to view osmosis not just as a passive chapter in a biology textbook, but as a dynamic, relentless engine that powers both life and technology.
It is the ultimate reminder that the most powerful forces in our universe aren't always the loud, violent ones. More often than not, it's the silent, microscopic balancing acts that hold the entire physical world together.
I couldn't agree more. Thank you for joining us on this deep dive, tracing the journey from a top piece of pig leather to the invisible mechanics of the virial theorem, all driven by the simple, unstoppable desire of water to find its equilibrium.
And before we go, I want to leave you with one final, slightly futuristic thought to mull over.
Okay, let's hear it.
We've talked about how forward osmosis can perfectly filter water using consumable draw solutions without heavy electrical pumps. Now imagine a multi-generational interstellar spaceflight decades away from Earth.
Power and replacement parts for mechanical pumps will be incredibly scarce.
Exactly. So, could the key to long-term survival in deep space rely on closed-loop osmotic systems? Could we design artificial, membrane-based ecosystems aboard starships that perfectly mimic Earth's water cycle, recycling waste into drinking water entirely through passive, silent thermodynamics?
That is fascinating.
Or even further, could specialized engineered microbes utilizing osmotic pressure be deployed to terraform the toxic heavy metal soils of distant exoplanets, literally bulldozing alien environments into habitability one microscopic drop of water at a time?
Now, that is a deep dive worth taking. Keep questioning the invisible forces running the world around you, and as always, stay curious.